All right, some more problems here. So C2H4. Let's try this one. Let's get the valence electrons count. So for carbon, well, there's 2 of them, and they're good for 4 each. It's in column 4, carbon is on the periodic table. Hydrogen, remember, is always 1 valence electron, and there's 4 of them. So that's going to get me 8, that's 12 valence electrons. Hydrogen never can be a never can be a center atom. It's always going to be on the end or terminal atom. So the skeleton is going to have to look something like this. You know, usually you always want to put something that's very symmetric. I mean, you could, in theory, write, you know, maybe you would start out with something like that. But, you know, in general, molecules like to be symmetric if you don't have any other information, okay? So let's not worry about something that looks like that. Let's look at something that's symmetric. Carbons we know are going to be in the center, again, because hydrogens have to be on the end. So now let's connect these with single bonds. So those are each good for 2 electrons. So you're at 2, 4, 6, 8, 10 electrons. Well, we have 12 total valence electrons, and let's see what would happen here. So let's just put, to start out, a lone pair, right? Now we'd be at 12. Let's see, do we satisfy the octet rule? 2, 4, 6, 8. This carbon's good. All the hydrogens are good, of course, because they're duet rule. And this carbon, 2, 4, 6, not good, right? So that means we're going to have to erase this double bond, lone pair, and make it a double bond. And now we're good. Every carbon has 8 valence electrons. 2, 4, 6, 8. 2, 4, 6, 8. Okay? And so now the next part of this was, that's our Lewis structure. The next part of this was to come up with the steric geometry. Steric geometry here is, well, this is symmetric molecule. So something we say for one carbon is going to be the same for the other carbon. So we only really have to do this once. Steric geometry here is what? Number of bonding sites plus lone pairs. There's no lone pairs. So we have 1, 2, 3 bonding sites. And so that's going to make us trigonal planar. And there's no lone pairs. And since there's no lone pairs on any of the central atoms, that's also going to be the molecular geometry. And that tells you that you're going to have a bond angle of 120 degrees. So all these are going to be 120 degrees, ideally, okay? It turns out there's some slight differences here, but for the sake of this course, we don't care. It's because the double bond, it behaves differently than the single bond. So, but you know, for us, if there's no lone pairs, we're going to call this 120 degrees all the way around. Just know that in reality, that's an approximation. I mean, I'm just telling you that. You don't have to know that. Okay. Let's do this one. So this is the bromine ion anion here. So this one's a little different in that it's an ion. So let's do valence electrons. Bromine is a halogen. That's good for 7. Oxygen is good for 6. There's 4 of them, but we have to add 1 because it's a -1 charge, right? So we have 7 plus 1, that's 8, plus 24, that's 32 valence electrons. Bromine's going to be in the center here. It's less electronegative than oxygen. And so now we can kind of tie our 4 oxygens around first with single bonds, and let's see what happens. This is the whole thing's a negative charge, so we put a bracket negative charge. It's an polyatomic anion, right? Okay, so we have 32 valence electrons, and we need to satisfy the octet rule. So we're going to put 6 lone pairs everywhere for our oxygens, and let's see if this sounds good. 2, 4, 6, 8. That's 1 oxygen, right? It counts for this whole oxygen plus the bond, and we have 4 of those. So that's good. 8 times 4 is 32. We're done. Now we just need to do steric number. Steric number, remember, is number of lone pairs on the central atom plus the number of bonding sites. So there's 1, 2, 3, 4 bonding sites. There's no lone pairs on the central atom. Steric number 4, that's going to get us a steric geometry of tetrahedral. There's no lone pairs on the central atom, so we're not removing any vertices from the tetrahedron. So it's going to also be tetrahedral for the molecular geometry. That's the shape, okay? And then the bond angle is going to be the idealized bond angle, again, because there's no lone pairs on the central atom, so it's 109.5, okay? And so really how I drew this, you know, it isn't great because that's kind of assuming that it's a plane. Again, you don't need to know the wedged dash notation for this course. You will if you take organic chemistry, but a better way of drawing this just for your own knowledge, not asking you to know this for the course, would be like this, okay? And again, this is an anion, so it'd be like that. But that's telling you that this oxygen's sticking out of the paper, and this oxygen's going pointing backwards, okay, beyond the slide. And these ones are in plane. So that gets you that tetrahedral type shape.